Hello everyone. If you are struggling with your organic chemistry preparation, this video is perfectly fit for you. Similarly, if you are doing the revising the concept, attending the mock test series, this video is for you. Don't skip any part. We are going to cover entire organic chemistry from 11th and 12th in this single video. This video gives lots and lots of information, tips and tricks, the main points to cover for organic chemistry for your competitive examinations. We are going to cover GOC and isomerism, hydrocarbons, halocompounds, alcohol, phenol and ether, carbonyl compounds, amines and biomolecules as well. So this video will be very useful and very important. So if you watch this video till the end, after this, maybe this is a long video, but after this video, you should be able to solve the problems on straight. Get those marks on straight. So that is our aim. So please do watch carefully, side by side, take the notes, or you can download the notes as well. But if you are a student who already know every concept, you can start attending the mock test link. The mock test link is given in the description. You can start attempting those mock tests. There are 30 mock tests and then 5 full test papers are there. So you can just attempt it and know your scores. Okay, so without any further delay, let's get started. The first thing first, GOC and isomerism. So the questions may be asked from the simple concepts like electronic effects. So what are those permanent effects? Permanent effect. Those are inductive effect, mesomeric effect or resonance effect, and hypoconjugative effect. And what about the temporary effect? This is asked in one of those papers. Which of the following is temporary and which of the following is permanent effects? So only one, that is electromeric effect. That is our temporary effect, because upon the value or of the opponent, or you can say the incoming reagent decides what have to happen in the present hydrocarbon. That is what the electromeric effect is, right? So if you're not sure about any of these concepts, you can look back. We have given each and every chapter as a crash course, as a separate video. Here we are going to cover only the important concept and just a revision part. Okay, so temporary effect, permanent effect sorted. Okay, so how we can find and what questions can be asked? So in case of inductive effect, it is by the plus inductive effect means electron releasing group, minus inductive effect means electron accepting group. Okay, and in case of mesomeric resonance, or resonance, which is very important upon deciding the stability of the compound, right? So you can remember it like this. All those electronic effects, you can remember it like a name, Rohit. Okay, R stands for resonance, H stands for hypoconjugation, I for inductive, and T for temporary effect, that is electromeric effect, is leave it. So R, H, I, these three are very important. So this is the order to decide the stability. Okay, so most of the questions will be asked from R, resonance effect and inductive effect. In better cases, you can expect the questions from hypoconjugation also. Hypoconjugation is nothing but number of alpha hydrogen increases, the stability will also get increase. Okay, then what else can be asked? You can expect the questions in case of conjugated system, in case of resonance. So the types of conjugated system, we know pi bond, alternate category, like this, alternate pi bond category, or which one is more stable? Of course, whichever undergoes the complete conjugation, that would be more stable than the another one. And if you are talking about the ring system, that gives you more stability. Conjugation, ring system, and you have to check for the aromaticity as well. Okay, so aromatic, and then comes non-aromatic, and then anti-aromatic. And some questions can be asked, which of the following is more stable, given that the plus and minus sign. So in this type of questions, please remember few things. One is that more the charges, less stable. The stability will get decreased. Okay. The second thing is electronegative atom should get electronegative atom like fluorine, chlorine, bromine, iodine, and oxygen as well. Electronegative atom should possess a minus charge, negative charge. Okay. And electropositive atom should get a positive charge. That gives you more stable, more stability. Okay. Then the questions can be asked from intermediates as well. So which of the following intermediates are stable, or which of the following carbocation is stable? Okay. So in that case, you have to remember, in case of carbocation, tertiary is more stable than the secondary and comes primary. Okay, tertiary carbocation, that is more stable than the secondary, then comes our primary. So order of electronic effect we know, mesomeric, and then comes hyperconjugation, and then inductive effect. So if they are asking for the stability, the order of reactivity, I am giving you this order for alcohol. Okay, because the most of the questions asked from alcohol, because in alcohol you can expect a hydrogen bond. So obviously the extra bond will give extra stability. So solubility of alcohol increases with branching, right? So for example, N-pentyl alcohol, then comes iso, then comes our neo. This is a stability order. And reactivity order, if you are considering the reactivity order, primary, then comes secondary, then comes tertiary in case of OH bond fission. Okay. And if they are asking about CO bond, because alcohol, the carbon is attached with oxygen, oxygen is attached with hydrogen, right? If they are asking about CO bond fission, then tertiary, secondary, and then primary for CO bond fission. These points will help you for determining the which is more stable, or the questions can be asked which requires more energy to break down, that kind of type. The third point is that the same order for dehydration as well. The questions combined with physical part to organic, these 3 points will be very much useful to you. Okay. And point to be noted, I'm giving you the few points in case of reaction mechanism. All positive charged species are electrophiles. But there is an exception, except ammonium and hydronium ions. So except these, all positively charged species are electrophiles. Electrophiles means electron loving species. Okay. And greater the number of alpha hydrogen, as I told you, the number of alpha hydrogen increases, it becomes more stable. Then the third point is that in case you are looking for the order of inductive effect, the minus I order will be, mostly they will be asking questions from nitro, cyano, and carboxylic acid group, fluorine, OH. And then comes our benzene, the phenyl ring, and CH double bond CH2. In case of plus I effect, the order goes like this: NH minus, O minus, COO minus. These are tertiary alkyl groups, then comes secondary, then comes primary alkyl group. So others, you can say that electron withdrawing group, the normal electron withdrawing series and electron donating group. But in case of inductive effect, that is a bit different, isn't it? So here you can see the difference. Mostly inductive effect, these 3 points are tertiary, secondary, primary. This case is very, very, very important. And in case of minus inductive, nitrocyano alkyl groups are very important. Okay. Let's move on to the next part. The next part, which is of the next part, we are going to see that is nomenclature. So the normal nomenclature, I'm not going to talk about it. I'm just going to talk about the complex one. Okay. So the first point, while they are having more substituents. Okay. So normal one, you can easily name it. I know you know everything. The complex one, let's say I'm having the complex like this of CH3, CH2, CH2, then C with CHO and another CHO, CH2, CH3. Let's say the compound is like this. How we have to name it? What is the name of this compound? If you know, just put it in. Okay. So if a compound has only two search functional groups, then carbon of one functional group will be the one terminal carbon. And the carbon of the another functional group be the another terminal carbon of the principal chain. Okay. So how we have to number it then? 1, 2, 3, 4, 3. So how we have to name it, number it then? If a compound has two such functional groups like CHO, CHO attached with the same carbon, then one group will be the terminal carbon and the another group will be another terminal. Okay, so this will be our principal chain, remaining are substituents. Okay, so the name of this compound, which is having only 3 carbons, so which gives the name as pro. Right, so remaining you can easily fix it. Here I'm having 1, 2, 3 groups, and this side I'm having ethyl group, another side that I'm having propyl group. So you can easily fix that. Okay, so let me give you one more problem, which is COOH, CH3, C double bond O, CHOH, C double bond O, COOH. Ma'am, what is this mix of functional groups? Yes, I know. Just try to name it. If two substituents at carbon 2 of the principal chain, which is principal chain by the way here, so which includes the priority functional group, right? What is the priority functional group here? That is COOH group. So the two substituent at carbon 2 of the principal chain, that is here we are having ethyl and propyl. How to name this compound? If we are having two same functional group attached with the same carbon. Okay, so in that case you can take one of those functional group as in one terminal, the another functional group as an another terminal of the principal chain. Okay, so in that case 1, 2, 3 is our principal chain. So the name of the principal chain is propyl. The remaining, the two substituents at the carbon 2 of the principal chain, that is one side I'm having ethyl, another side I'm having propyl group. So the name of the compound becomes 2-ethyl, 2-propane for the principal chain, and dial. Okay, let me write it below. So propane, so that is the name of the compound. Okay, so let me give you another example. Just try to do this one. COCl, CH2, CHOH, COCl. So in this case, how will you name it? Okay, so just try to name it and put it in the comment section. I'll reply immediately. Then the second condition we are going to talk about is if a compound has more than 2 like groups, then 2 functional groups are treated as a principal functional groups. Right. So the simple one I can give you, that is CH, 2COOH, CHCOOH, CH2COOH. Then how will you name it? Butane, 1, 2, 3, tricarboxylic acid. Correct? So this is an important question which was asked in previous year papers. Okay. So similarly, you can try it out with other functional groups as well. Okay. So if the carbon of the functional group is not included in the longest possible chains. And all the functional groups have highest priority, should be treated as a principal functional groups. Okay, like this. For this, I can give you another kind of example, that is CH2COOH, CHCOCl, and CH2COOH. How will you name this? Which takes more priority? Of course, COOH groups takes more priority. Then, how will you name it? The name of this compound is 3-chloroformyl pentane. Why pentane? Because we are counting over here. Pentane. In which position am I having the carboxylic acid? 1,5, isn't it? So 1,5 dioic acid. Okay. So this is about the important parts. I just want to let you know about nomenclature. The next thing we are going to cover, that is isomerism. In isomerism, we already have the entire discussion. Just I'm going to give you the glimpse of it. How to name this compound? If we are having two same functional group attached with the same carbon. Okay. So in that case, you can take one of those functional group as in one terminal, the another functional group as in another terminal of the principal chain. Okay. So in that case, 1, 2, 3 is our principal chain. So the name of the principal chain is pro. The remaining, the two substituents at the carbon 2 of the principal chain, that is one side I am having ethyl, another side I am having propyl group. So the name of the compound becomes 2-ethyl, 2-propane for the principal chain, and dial. Okay, let me write it below. So propane, so that is the name of the compound. Okay, so let me give you another example. Just try to do this one. COCl, CH2, CHOH, COCl. So in this case, how will you name it? Okay, so just try to name it and put it in the comment section. I'll reply immediately. Then the second condition we are going to talk about is if a compound has more than 2 like groups, then 2 functional groups are treated as a principal functional groups. Right. So the simple one I can give you, that is CH2COOH, CHCOOH, CH2COOH. Then how will you name it? Butane 1, 2, 3 tricarboxylic acid. Correct? So this is an important question which was asked in previous year papers. Okay. So similarly, you can try it out with other functional groups as well. Okay. So if the carbon of the functional group is not included in the longest possible chains, and all the functional groups have highest priority, should be treated as a principal functional groups. Okay, like this. For this, I can give you another kind of example, that is CH2COOH, CHCOCl, and CH2COOH. How will you name this? Which takes more priority? Of course, COOH groups takes more priority. Then, how will you name it? The name of this compound is 3-chloroformyl pentane. Why pentane? Because we are counting over here. Pentane. In which position am I having the carboxylic acid? 1,5, isn't it? So 1,5 dioic acid. Okay. So this is about the important parts. I just want to let you know about nomenclature. The next thing we are going to cover, that is isomerism. In isomerism, we already have the entire discussion. Just I'm going to give you the glimpse of it. In case of isomerism, it is divided into 2 parts, right? Structural and stereo. Just I'm going to explain what is what and what are the questions can be asked. So the first thing, in case of structural isomerism, the simple questions can be asked from positional isomerism and functional isomerism. Okay, so by giving any molecular formula, you can expect which of the following this molecular formula can exhibit. Okay, then positional isomerism means the functional group, the placing of functional group differs. Functional group isomerism is nothing but functional group changes. The fourth isomerism, that is metamerism. This is important because in case of metamerism, the functional group must have two parts. Two alkyl chain can be attached. For example, keto. Okay, so or ester. So that kind of example works for metamerism. Okay. Then our tautomerism. Tautomerism you very well know. Keto, enol tautomerism, nitro, nitrito tautomerism. Those things you know. Then coming to stereo part. Here we have conformational and configurational. So what is this? Most of the students will get confused in this case. Conformational and configurational. In configuration only we have optical isomerism and geometrical isomerism. Okay, so they may confuse it as well. Optical and geometrical. Let's see more about this stereo part. Okay, so the first thing first, stereoisomerism means the spatial arrangement will get differ, isn't it? So in case of configurational, we have geometrical isomerism. So which will exhibit geometrical isomerism? Of course, our double bond compound, which are having restricted rotation in it and which should be attached with the different groups as well. For example, these two groups must be different, but it can have a same group on different carbon. Please take care of that. Not only the double bonded compound, it can be exhibited this case of chains as well, like this. This one, and this is an isomer of the another one, which will have restricted rotation. That's why it can't be interconvertible. These are having restricted rotation. Okay, so in this case, the question can be asked from cis and trans, right? So what is cis? What is trans? Cis means same side. Trans is opposite side. Okay, ma'am, but I don't know where I have to name cis and trans and where I have to name E and Z. Right? So many times you will get confused between these. Cis and trans is for similarity of the groups. But in case of E and Z, it deals with the seniority of the groups. This deals with seniority. We number it, no? 1, 2, the priority order we will give. I'm not talking about RNS. Priority order will give. In that case, you have to use E and Z. Z is for same and E is for opposite. The same priority groups, if that is an opposite side, then the E. If that is on the same side, then that is Z. Okay, so you can remember it like Z is having very similar method of writing as S. Okay, Z is same. Okay, so that rule you can follow, and CIP rule is for R and S notation. Correct? So where you have to follow certain rules. The first thing is higher molecular weight. Then the second rule is higher mass of isotope. And the third, which is that if the first atom of the group is identical, then you have to go for the second atom. The fourth rule you have to follow, that is, if the group is having double or triple bonds, then you have to consider that many groups are there. Then the fifth rule is that the bond pair gets more priority than the lone pair. Don't worry guys, I'm attaching these notes in the description. You can download it. And E configuration is less priority than the Z configuration. Clockwise means are anti-clockwise or counterclockwise? That is yes. And point to be noted, the H should be on the least priority position. If they are giving about the 3D structure, that should be behind the plane. The least priority group should be behind the plane. Not only H, the least priority group. It can be of lone pair also. So least numbered or least priority group or should be behind the plane. If that is not like that, then you can switch the R and S. Okay, then H must be on the horizontal position if they are giving the structure like this. Okay, so that's about the CIP. Then we are moving on to optical isomerism. Optical isomerism, definitely you can expect the question for chirality or enantiomer diastereomers. I'll tell you. So chiral carbon means all four groups are different, right? So all four groups are different. Then you have to check these chiral groups will have optical activity. Optical activity means whether if you are passing the molecule with a plain polarized light, it will rotate the light either clockwise or anti-clockwise. If that is rotating, then that would be optically active isomer. Okay, so enantiomers, which is non-superimposable mirror images, and diastereomers, they are non-superimposable non-mirror images. Okay, we already discussed isomerism part. I don't want to get into more detail about those things. This can be your checklist. Okay, so just give a glimpse, and this is the time to do the mock test. Once again, I'm reminding you, I'm giving the mock test link, which will have 30 papers and 5 full test papers. You can download it or you can answer it there as well. So check your scores and how well you have prepared. Okay, so let's move on to the next part, that is the conversions. If you're confused in case of conversions, it's time to clear it. Okay, let's say they are giving Fischer projection. Fischer projection means how that will look like. It will look like this, right? So COOH, let's say they are giving you the compound like this, OH, COOH. They are asking you to convert it to Sahas. So Sahas projection means first what we have to do, first write the chiral carbon. So there are 2 chiral carbons, isn't it? So I'm writing these 2 are the chiral carbon of the given molecule. After that, change the position of the second chiral carbon if both are on the same side. Okay, so this is in the, I'm writing here COOH, H, OH. Then another side I'm having COOH, changing the position to OH, H, because you are seeing from this side. Okay, so this carbon is the projection from another side, this carbon is the projection from this side. Or else you can write it as these 2 are chiral carbons, COOH, one side I'm having OH and another side H. This is for one carbon. Another carbon COOH, H, OH. Okay, so this is the conversion of Fischer to Sahas. Then how will you convert Newman to sawhorse. I'm giving you the same kind of example. COOH, OH, OH, H. So this is Newman projection. I'm going to convert it to sawhorse once again. So how will you do that? Directly you can't do the conversion of Newman to sawhorse. First you have to convert it to Fisher. So for converting to Fisher, I'm writing it like this. COOH. Another side I'm having COOH. So for this carbon, so COOH to the left side hydrogen, right side OH. From here OH and H. But this is an inverted way. So you have to be careful about that. OH and this is H. Right? So now we are going to, or else you can, if you want to convert it directly, you can write it like this. COOH, HOH for this carbon, and then another one which is a rear carbon, that is circle refers to the rear carbon. So OH, H, COOH. Okay. So in worst case, they can ask the questions from conversion from formula. Please be prepared for that. Apart from that, the important points I'm giving you for the conformations, conformational isomerism. So here N-ethane and N-butane is more important. So in case of, the main thing you have to remember, that is, in case of ethane, there are only two conformations, that is staggered and eclipsed conformation. So which one would be more stable? That can be of your question, staggered and eclipsed. So the staggered one, which is having more or less of a strain than the eclipsed one, which makes it more stable in case of ethane. So the questions can be asked from N-butane as well. So that will give you the different configurations, but I'm giving you the stability order. Anti, which is on CH3 groups of the opposite side, then gauche, eclipsed, then comes fully eclipsed. Okay, so that is the order of stability. If they are asking some other compound, check for the hydrogen bonding as well. Then cyclohexane. In case of cyclohexane, if I'm drawing a cyclohexane structure like this, here we have axial and equatorial positions. The trick is that if the bulky groups present in the axial position, that is not at all stable. Okay, so the questions can be asked in that way. This is axial, this is equatorial. This is axial, this is equatorial. Axial, equatorial. Equatorial, axial. Okay, so please be careful. Axial position, the substituent should not be present. That way, reduce the stability of the compound. Okay, so that is about the hydrocarbons. GOC and isomerism. Let's dive into hydrocarbons. So in case of hydrocarbons, we know very well about the formulas like alkanes, alkenes and alkynes. Let's look into some important reactions in hydrocarbons chapter, then you are covered. Okay, so the first reaction is that hydrogenations to prepare hydrocarbons. So the hydrogenation can be of two kinds, heterogeneous and homogeneous. Homogeneous means the phase and the reactant would be of the same phase. the catalyst and the reactant, which would be on the same phase, but in case of heterogeneous, that would be different. That is the major difference between these two kinds. For example, if I am taking a molecule like this, I am undergoing the hydrogenation with hydrogen, palladium, or nickel, or platinum. You can use. I am taking palladium here. So what will happen? Addition of hydrogens. So R, CH2, CH2, R. So this is a hydrogenation. You have to add the hydrogens on the unsaturated carbons. Okay. The second reaction, you can prepare it from alkyl halides. The important reaction here, that is Woods reaction. So Woods reaction, we are taking two same alkyl halide and preparing a hydrocarbon in the presence of sodium and dry ether. This was asked in a previous year paper as well. So this can't be prepared. This method will not give you the lower, let's say methane you can't prepare. Okay, after 2 carbons only you can prepare through this method. Okay, so what if I want a different hydrocarbon? Then you have to take a different molecule, R dash, you can prepare. There is another reaction accompanied with this, that is fitting reaction, where you can prepare it from aryl halides. Sorry. So this will give you the phenyl ring attached with another benzene ring attached with another benzene ring. Combining these two reactions, Woods and fitting, you can prepare Woods fitting reaction plus Rx. That will give you the alkyl group attached with the aryl ring. Okay, so this is one of those methods, and these are undergoing ionic mechanism and sometimes free radical mechanism as well. There are 2 types of mechanism it would follow, ionic and free radical. Then from Grignard reagent, so RMgX, you can prepare our hydrocarbons. RMgX with H2O, that will give you RH, ROH also, that will give NH3, that will also give our hydrocarbons. RSH, or you can take RCOOH. All of these will give our RH. The byproduct, product with the Grignard reagent with Mg will be the different one, but all of these will give you the hydrocarbons. The next important named reaction, that is House alkane synthesis. Here we are taking REX treated with lithium. This alkyl group can be of primary, secondary and tertiary, no matter what. This will produce carbanion with lithium plus, because lithium is more electropositive when we are compared to carbon. Treating it with copper halide, it will give you a reagent, that is RCuLi, Gilman's reagent. Okay, this reagent is used in other reactions as well. But for example, if I am taking Gilman reagent with another alkyl halide, then that will give R dash. Okay, so this kind of reactions, this that Franklin reagent, so which is very similar to Woods reaction. Here you can see I'm taking Rx alkyl halide with zinc and Rx. Okay, so in the presence of ether, it is giving us higher alkanes. True. So along with that, I'm getting zinc halide. Okay, so this follows the formation of organo-zinc compound as its intermediate. Okay, so the Gilman reagent is important. Wood's reaction is important. You can see the Franklin reagent as well. In Wood's reaction, we used sodium. In Franklin, we are using zinc. And one more information I want to tell you. In the previous Gilman reagent, it is following SN2 mechanism. Okay, so SN2 mechanism to form R dash. Okay, so SN2 means obviously what? Primary and secondary is more favorable than the tertiary, right? Mostly tertiary will not give. Primary and secondary is more favorable. Gilman is following SN2 mechanism. Okay, cool. Then the next method is reduction of alkyl halides. We have seen hydrogenation and the substitution we saw. Then we are seeing reduction. First reduction. So first of all, what are the reducing agent we can use? I'm just giving you the reducing agent. So question can be asked by using the different reducing agent. Zinc with acid, or zinc with copper H2O, or zinc with copper plus acid, or you can take zinc with copper alone, which can be used as a solvent of C2H5OH, alcohol. Okay, and most important reducing agent, that is sodium amalgam acid. We are going to see this reaction in few minutes, but if you know what this reagent, this is a very important reagent. We have seen a name reaction as well for this reagent. Please tell me in the comments what that reaction is. Okay, so how the reduction happens? I'm taking Rx reacting with metal acid, which will give you RH plus HX. So this is the reaction. Then what if I'm having metal hydrides, Rx with phenyl tin hydride, that will give you again RH. So this type of reactions like triphenyl tin hydride, it reduces primary, secondary and tertiary alkyl halide. Okay, then you can use sodium borohydride as well. Sodium borohydride, the same reduction, but I'm telling you this will holds true for secondary and tertiary. If I'm taking lithium aluminum hydride, that can give two type of reactions. One is lithium aluminum hydride with alkyl halide, that is primary and secondary, that will give you RH. Okay, so if that is tertiary alkyl halide, then that will give you alkene. Okay, so this, although the lithium aluminum hydride is a strong reducing agent, tertiary alkyl halide will give you alkenes. Then the next reducing agent is that red phosphorus HA. So it is again a very strong reducing agent. So if I am treating RCOOH with red phosphorus, and if I am treating RCOCl with red phosphorus, or RCOOET, what is that, ester, so with red phosphorus, or if I am taking alkyl halide also, these guys will give RCH3. Okay, R group remains the same. Instead of those functional group, you will get CH3 group. If I'm taking Rx, that will give you RH as usual. And if I'm taking ROH, that will give you RH plus H2. Sometimes the byproduct will also be important. Then the next reaction with soda lime. This is important because the big question part, this is reacting with this is reacting with that. So in that case, this can be given as a clue point. Don't worry, your examiner will ask you simple questions only, but please be prepared. Okay, so soda lime, first of all I'm taking carboxylic acid reacting with NaOH. What that will give? Base with acid, ONA, right? So again I'm treating it with CaO NaOH, so which will give you R minus and Na2CO3. This R minus with H2O will give you RH. Here this step is rate determining step. Okay, so reaction with acid with base, where that is forming RH, that is important. The next reaction is super important, that is Globe's electrolysis. Electrolysis. Here you can expect a question which is anode, which is cathode as well. Okay, so which is nothing but RCOOK with 2H2O I'm taking. It is undergoing electrolysis to produce RR with CO2, H2 along with that KOH will be formed. Okay, let's say I'm taking CH3COOK, then that will give you CH3CH3. Okay, so that will be this reaction, and if the N is the number of carbon atoms in the salt of carboxylic acid, the alkane formed has, here if I'm taking N as this molecule, then the formation of product which will be having 2 N minus 1 carbon atoms. Okay, so through this way you can predict a product easily. Then I told you guys what is that reagent, zinc with mercury. So RCHO, zinc, mercury, HCl, zinc amalgam, which will give you RCH3 with H2O. So if I'm taking RCOR as well with this reaction, that will give you RCH2R. What had happened over here is this C double bond O of the carbonyl group is got converted to CH2. That is a easy trick you can remember. Okay, so this reaction is called Clemmensen reduction. Clemmensen reduction, and the one more important point you have to remember here is acid medium only it will react. This will not go about basic medium, and if there is a functional group or if there is a group which can be affected by acid, then this reaction will not give you the desired product. Then what we can do is you can go with Wolff-Kishner reduction. So Wolff-Kishner reduction, which will can be used to go with acid sensitive functional groups as well, because where we are using base. Let's say I'm having RCHO, the reagent is hydrazine with KOH, that will give you RCH3, hydrazine with KOH. Next, in this part, in the preparation properties of alkane, you very well know about free radical reactions like monochlorination. Just look into it. I'm giving you the reactions. It comes under the upcoming chapters as well. So monochlorination, aromatization reaction. And the third checkpoint is that combustion. You can look under general formula of the combustion. You know, right? The general formula CXHY plus X plus Y by 4 O2. Upon combustion, it will give you XCO2 plus Y by 2 H2O. The next thing we are going to see, that is alkenes. Alkenes, general properties, the melting point with increases with increase in molecular weight. The boiling point is also increases with increase in molecular weight. The melting point of trans structure will be more than the cis. Similarly, if I am considering the boil point, cis will have more boiling point than the trans, because the branching decreases the boiling point. In case of melting point, the packing capacity affects the melting point. Okay. Then just to simply, if they are asking for the stability, as I told you, you can go about trans is more stable than cis because of van der Waals repulsion. Cis is having more van der Waals repulsion than the trans. Due to that, the stability of trans is more than the cis. Okay. How do you test? Test for alkanes is very simple. Either you can go about with bromine water, the decolorization happens, or you can go with cold KMNO4. In both the cases, it decolorizes. Okay, so one more clue point if I want to give you, it can undergo ozonolysis. Ozonolysis to give carbonyl compounds. Okay, that can be given as a clue point. Okay, so next preparation part. Preparation of alkanes. Of course, it can undergo, it can be prepared by the addition of hydrogens. Hydrogenation can take place. The one more important catalyst in case of alkenes, you have to remember Lindlar's catalyst. So Lindlar catalyst is nothing but hydrogen with palladium calcium carbonate. Okay, and quinoline will be there. So it's just a hydrogenation happens, R, C, triple bond, C, R, Lindlar catalyst, which will give you R, double bond C, H. Please remember, this is giving us cis product. Okay. So cis product can be obtained from this catalyst. And if you want trans, then you have to go with bridge reduction. Bridge reduction will give you trans. So what is the reagent where we have to use is that just you can use lithium with sodium and liquid ammonia. So the trans product will be formed. Okay. Then it can undergo halogenation of vicinal dihalides. Those parts you already know about that. And the next reaction is that oxymercuration, demercuration. What is this? Oxymercuration, demercuration. So generally, the alkene is reacted with mercury, which is having a C double bond O, CH2 twice. The solvent can be non-polar solvent, which is used, THF. So this will give you the product of H and OH substituted product, like this. Okay. The demercuration, oxymercuration and demercuration will give you the H2O substituted, or you can consider that as a OH and hydrogen substituted product. So can you tell me the product for this reaction? CH2 double bond, CH, CH2, CH3 with mercury OAC2, H2O followed by sodium borohydrate. This is 1-butane. Can anyone tell me the product of this reaction? Just give it a try. Okay, the next reaction we are going to see, that is hydroboration followed by oxidation. So in case hydroboration, so boron will be there. So what is this reaction? Alkene with BH3 THF. That will give you syn addition. Okay, anti-Markovnikov rule will be followed over here. Again, this is a HOH addition only, but anti-Markovnikov rule is followed and the product is syn product. Okay. Then as I told you, we have ozonolysis. Ozonolysis means I have already told you, if you are having double bond C, then you have to do with break the double bond, put double bond O over here. So you will be getting a product like this. Okay. So in case of alkene, it will give you two products. Then the next reaction, that is with permanganate. So let's say I'm having alkene like this. Permanganate will always give you syn addition. Okay. So this is a reactant KMnO4, one concentrated KMnO4. Okay. So what could be the product is that, so this will obviously break the double bond, put double bond O, and another side you will be getting a carboxylic acid. Oxidation had happened over there. So let me erase this. Double bond O. Remaining, I'm having COOH. Okay, this carbon becomes COOH. So oxidative product will be formed. So what if that happens in the ring system? So let's say I'm having a ring like this. Here also I'm having a double bond. In the ring also I'm having a double bond. Treating it with KMnO4, it will give you what should happen? Break the double bond. Oxidative ozonolysis should happen, right? So the oxidation should happen. So here there is no substitution. Put COOH group over there. So it will be formed COOH, and here also COOH. Then what about this carbon? Once again you have to break the bond, remaining this carbon, and here you can put double bond O. But still I'm having a carbon over here. That will be left as CO2. Okay, so this is our reaction with KMnO4. The next one we are going to see, that is alkynes. Okay, so in case of alkynes, what are those general properties? Once again, melting point, boiling point, which we already know. So if I'm comparing the pKa value of alkenes and alkynes, alkynes will be the least, and then comes alkenes, and then our alkanes. Okay, so I'm giving you the table also to compare the all three hydrocarbons. We already posted the formula sheet as well. What are the tests to confirm alkynes? Is that, as I already told you, bromine water test, cold KMnO4 test, that will give you the decolorization. Ozone, that will also give you the oxidation reaction. Apart from those three, still we have one more test for terminal alkynes. Terminal means if a triple bond is in the end. Okay, so in that case, you can use cuprous chloride with ammonium hydroxide. This will give you red precipitate. So why that is forming red precipitate is because of those hydrogen in the terminal carbon. Let's say I'm having like this. This hydrogen is participating in the reaction to form RC triple bond C, Cu, not bond, Cu, which is a red precipitate. Okay, then one more reaction, that is you can treat it with silver nitrate, ammonium hydroxide. Since that is an acidic hydrogen, once again that will also give, the terminal hydrogen will participate, and that will give white precipitate. Sodium in ether, that is its third test, to give colorless gas, but that is also participating with our terminal hydrogen. It releases H2 gas. H2 gas you can test it with the pop sound, right? Okay, as I told you, that hydrogen is an acidic hydrogen. So it can react with metals or react with base to form a corresponding salt or ion. So in case of preparation part, Lindlar catalyst is for cis, bridge reduction is for trans products. What that will give? Alkyne to alkene. Okay, cis and trans depend on the reagent you are using. Then it can undergo hydroboration. It can undergo the addition of halogens to form the product. It can undergo hydroboration followed by oxidation reaction and oxidative cleavage as well. So in case of ozonolysis, it will not break the complete triple bond. Sorry, it will not break the triple bond. This will have a bond exist. Okay, so with KMNO4 also, RC triple bond C, or with KMNO4, this will give you RCOOH plus RCOO. Let's say if it is R dash, then this kind of product will be formed. So that's it about the hydrocarbons part. You can also check out the aromatic compounds. That is just about Huckel's rule, what you have to follow and which is more stable. The next part, which is aromatic hydrocarbons, we already know about our aromaticity. Huckel's rule we have to follow, and which is more stable, but I'm not going to talk about that. I'm going to talk about the reactions. The first reaction, that is electrophilic aromatic substitution reaction, which is very important because aromatic compounds will not give you SN1 or SN2 because of those partial double bond characters. Instead of that, it will undergo the separate reactions SNAR. Here we are going to talk about those apart from EAX. So first of all, electrophilic aromatic substitution, which can be of nitration, NO2 substitution, NO2 is acting as an electrophile, sulfonation, where SO3H is our electrophile, halogenation, halogens is negative no ma'am. Here it is acting as an electrophile. Then comes the two type of Friedel-Crafts reaction. One is alkylation, another one is acylation. Okay, in alkylation, R group will get substituted. In acylation, COR group will get substituted. Okay, so these are the types of electrophilic aromatic substitution. So what kind of question we can expect is that they will give you the reactant, they will give you this is what is going to happen. They will ask you to predict the product. For that, you have to know about electron withdrawing group and electron donating groups. Why? Because there are two scenarios in case of substituted aromatic compounds. So the first one is orthopara substitution. Orthopara directing. Sorry. So orthopara directing groups. And another one is meta-directing groups. We already posted a video on this in detail, but I'm telling you orthopara directing groups like OH, NH2, if that is present in the ring, which will direct the incoming electrophile like nitro, sulfonation or halogenation, those incoming electrophile to an ortho and para position to that substituent. Okay, so for example, if I am having aniline, if I want to substitute it with nitro group, okay, so this will direct it to either ortho or para. Similarly, in case of meta-directing group, this will direct the incoming electrophile to meta position. But where that happens? Usually, the electron donating groups will give you the orthopara directing direction, and electron withdrawing groups like nitro, cyano, those groups will direct the incoming group to meta position. So these two are very important in case of electrophilic substitution case. Okay, so the next one, we are entering into 12th grade. So 12th grade we have halocompounds, right? So halocompounds which is having halogens in it. So alkyl halides and aryl halides. So we already know about these, how to name it, what are the isomerism it can exhibit, and so many things. Apart from that, what we have is that, so apart from the general isomerism and nomenclature part, here in halo compounds, we are going to discuss the bonding at the bond length. So if I'm taking a simple alkyl halide, CH3F and CH3Br and CH3I. So which will have a more bond length? So by comparing this, CH3F will have least bond length, because we know that bond length increases means strength decreases. So obviously fluorine, that is more electronegative and so small compound, so which will be closer to carbon CH3. Then comes our CH3Cl and then comes our CH3Br. Okay, so in case of bond length, this is smaller and then comes this and then CH3Br, finally CH3I. Okay, so then we are going to talk about boiling point. So with respect to the halogen in the group, the boiling point increases with dissonance in the periodic table. The alkyl fluorides will have a lowest boiling point and alkyl iodides will have a highest boiling point. Then comes our preparation part. Let's say the preparation of haloalkanes can start from preparing from alcohol. Alcohol, upon treating it with anhydrous zinc chloride and acid medium. This is a famous test called Lucas test. This test is used to distinguish primary, secondary and tertiary alcohols. Depending on the timing, how easily it can react, we can distinguish these three types of alcohols. Tertiary alcohol reacts immediately, then comes secondary, then primary alcohol. Okay, you can see the turbidity over there that indicates the reaction. Fine. Then the next preparation, that is with PCl5, it is forming RCl along with that POCl3 and HCl. And SOCl3, that is thionyl chloride, with that it is giving us SO2 and HCl. These two components are gaseous in nature, so that it easily evaporates from the eel solution. It indicates it is a more convenient way to prepare haloalkanes from alcohols. Okay. Then the third method, you can use PBr3 to prepare bromoalkyl alkanes as well. Okay. So let's move on to the next preparation, which is from alkene. So from alkene, I'm doing hydrohalogenation. X can be of anything, any halogens. So hydrohalogenation means hydrogen and halogen will be taking place, right? It will be added to the across the double bond. Here you can see this as a product. Another reaction, the second reaction, can you guess whether that is following Markovnikov addition or anti-Markovnikov addition? As I told you, Markovnikov addition means the hydrogen will get added to more hydrogen, more number of hydrogen side. It's a trick to remember it. Rich is getting richer, hydrogen is growing. So that is the trick. So here you can see this is following Markovnikov addition. Right. So if the presence of hydrogen peroxide and HBr2, this combo, we usually say certain combo, the music will hit. Right. So similarly, HBr and hydrogen peroxide or any peroxide combo will give you anti-Markovnikov addition. Anti-Markovnikov means H goes to the lesser H side. Usually we talk about Markovnikov rule states that the negative adenium part will go to more substituted side. That's what the rule is. But for remembering, I'm saying rich getting richer. Okay. Then the next method is that dibromination. So in this case, this giving us the trans product. Trans is giving this kind of product and cis is giving us a racemic mixture. Okay, so this is one preparation. The next preparation we are going into. Before that, I would like to let you know the dibromination reaction always happening in the anti-addition. Why that is happening in case of in the type of anti-addition? Because once the bromine is attached to the one of those carbon, it is forming a brominium ion complex. Okay, it's like this brominium ion complex. then the another bromine will attack on the opposite side of the existing bromine. So that's why the anti-addition is taking place in case of dibromination. Clear? This is very, very, very important question. Then the next method, as you know, that is from the silver salt, free radical mechanism it is following to form RBr. This is called Hunsdecker reaction. Then these two reactions, Wilkinson reaction and Schwarz reaction, these are very, 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 very important in this chapter, because Wilkinson reaction will only for iodides. You can take halobromide, you can take halochlorides, alkyl chlorides or alkyl bromides. Reacting with NaI acetone, the reagent is also important. NaI, sodium iodide with acetone, it will give iodoalkanes. Okay, so this is only for iodides. In case of Schwarz reaction, it is only for fluorides. Schwarz is only for fluorides. This is asked in, if I'm not wrong, this is asked in 2017 NEET paper. Okay, so the nucleophilicity order is same as iodine will be the leaving group. Order will be iodine leaves easier than the bromide, chloride and fluorides. These are following SN2 mechanism. Then the properties. The properties of alkyl halides. Here you can see the Woods reaction. We already saw that in hydrocarbons chapter. That is important. And with alcoholic KCN, the substitution happens. Alcoholic KCN. Okay. And ammonia, it is forming amines with sodium acetylene. It is giving us RC triple bond CH. Then NaSR. SR is getting attached with the alkyl groups. OCH3 getting substituted. SH is getting substituted. Aqueous KOH. Aqueous KOH means always substitution reaction. Alcoholic KOH means elimination reaction. Okay. Then again, NaI acetone, like we said for Wilkinson, Ri has been formed. Then the next set of reactions, here you go, are in AgCN. AgCN, it is forming NC. Right? RNC, not cyanide. RNC, because of the ionic nitrogen and carbon both are active sites. Right? Then KNO2 is for, where oxygen is getting attached with our alkyl group. That is as a major product. In case of AgNO2, nitrogen is getting attached with our alkyl group. So this is a major difference. The question can be asked from this part also. Then as I told you, alcoholic KOH, alkene because of the elimination reaction. Then dry Ag2O. There are two types of Ag2O can be used, moist and dry. Here we are using dry to get ethers. We'll do this in ether preparation also. With nickel hydrogen, alkanes are formed. Then benzene with AlCl3. R group is attached with the benzene ring. This is forming alkyl substituted benzene. Then alcoholic AgNO3 is forming AgX. And remaining RNO2 will be formed. Then the next one is haloarenes. Haloarenes, the important question can be asked, what kind of carbon is this? Here that is sp2 carbon. In case of haloalkanes, the carbon is sp3 carbon. Okay, and as I told you, this will not undergo SN1 or SN2. This is undergoing SNAR reaction in case of substitution because of partial double bond character. Partial double bond character between aryl ring and the X group. It is difficult to break that bond. In the preparation of haloarenes, you can see from benzene diazonium chloride, you can follow Sandmeyer reaction to give the product, and Gattermann reaction. The difference between Sandmeyer reaction and Gattermann reaction, the point to be noted is, here we are using CuCl HCl. In case of diatoman, just copper as a metal we are using. Okay. Then Ball-Schiemann reaction for fluoro compounds, fluorobenzene, and from benzene disonium chloride, Ki, it will give iodobenzene. Then halogenation part is undergoing electrophilic substitution, as I told you. In case of electrophilic substitution, one more point I'm giving you. This AlCl3, no? AlCl3 or any Lewis acid will be used, where it acts as the role of AlCl3 is to prepare a electrophile, because in case of Cl2, here I have AlCl3. Al is having a empty orbital in it, so that the Cl will come and the remaining one more Cl will become an electrophile. So this is how the electrophile is produced in case of this electrophilic substitution reaction. So these reactions we know already. Rastrick's process, which is where we are using benzene with HCl, which will give you chlorobenzene. The next one is nucleophilic substitution, SNAR. I have told you sometimes the question can be asked from this part as well. Why that is not participating in SN1 and SN2 reactions? Okay. Electron withdrawing group, if that is present, the nucleophilic substitution happens in the OH is replaced by Cl. Then the Dow's process to produce phenol from ARX can be of ARCl, ARBr. And then the second method with ammonia, it is giving aniline, and CuCN, it is giving us a cyanobenzene. Then electrophilic aromatic substitutions. Electrophilic aromatic substitutions, in this case, let's say Cl is present. Cl is in orthopara directus. It is deactivating the ring, but orthopara directus. So orthopara substituted products have been formed. One among the important products are DDT. Okay, uses of DDT can also be asked. Then reaction with metal, sodium, it is fitting reaction, Woods fitting reaction, and with magnesium, it is forming as a Grignard reagent. With nickel aluminium, it is forming benzene. So these are the important reactions you have to revise before giving the mock test. Okay, then uses, just a theory part, you can go through it. Now we are moving on to the alcohols chapter. So alcohols, we are going to talk about alcohols, phenol and ether chapter. So first thing first, alcohol is a OH functional group. The boiling point, the alcohol shows increase in boiling point with increase in molecular weight among the distillate homologous series. And alcohols do have higher boiling point than the hydrocarbons of the same molecular weight. Okay, let's say if I'm taking pentanol and pentane, so alcohols will have higher boiling point. Why that is happening? Because of intermolecular hydrogen bonding. Alcohols will have higher boiling point than the corresponding hydrocarbons because of intermolecular hydrogen bonding. Right? Then if I'm talking about the solubility in water, if the molecular weight increases, the solubility of the water will get decreases. The lower alcohols are easily soluble. If that is a higher level alcohols, then it is not much soluble because of, again, the intermolecular hydrogen bonding between alcohol and the water molecules. Okay, so you can see, let's say I'm having an alcohol like this. This is water molecule and this is alcohol. I'm taking these two. So the bond formed between the oxygen and the hydrogen. So this, because of this hydrogen bonding, it makes it soluble in water. Okay, so let's move on to the preparation part. First, from the halo, it is giving us the aqueous means, as I told you, this is substitution. Substitution taken place from aldehydes. Upon reducing, it will give primary alcohol. From ketone, if I am reducing it, it will give you the secondary alcohol. This is very, very important. We are going to see that in aldehydes chapters as well. From carboxylic acid, it will give you primary alcohols only upon reduction. Then esters, it will give you two type of alcohols depend on the R group we have taken. Then RCOCl, primary alcohol has been formed on reduction, and here also it will give you the primary alcohol but 2 moles. With Grignard reagent with formaldehyde, here you go, the reaction proceeds to form a primary alcohol. The R group will get attached with the aldehyde. With ketone, it is forming as a tertiary alcohol, because already in ketone we have 3 CH3 group. Again, this R group will get attached to the carbon, so it will form a tertiary alcohol. Then H2O addition. This is following Markovnikov rule in the acid medium. Hydroboration followed by oxidation. We saw that in hydrocarbons as well. So it is following anti-Markovnikov but syn addition. Then CO with H2 is giving us again an alcohol. Then the important reaction, that is saponification reaction to form trihydroxypropane, which is also known as glycerol. Okay, so the reaction is very simple. We are taking ester, treating it with base, it will give you salt and alcohol. Then talking about the chemical properties of alcohol, with red phosphorus iodine, it is just forming hydrocarbons. With ammonia, it is forming aniline. Again treated with ammonia, secondary amine, not aniline, primary amine, then comes secondary amine, then comes tertiary amine. Okay, so excess of ammonia, the reaction proceeds forward. Then with iodine NaOH, it is forming iodoform. As I mentioned, this is very, very, very important reaction, iodoform or haloform reactions with alcohol. And the reducing agents like, oxidizing agents like PCC, PDC, it will give you aldehydes. Okay, these are some mild oxidizing agents that can give you only aldehyde. If I am using strong oxidizing agent like K2Cr2O7 or permanganate, it will give you acids, carboxylic acids with the same number of carbons. If I am taking 2 carbon in the alcohol form, I will be getting 2 carbons only. Okay, with concentrated H2SO4, first H2SO4 will get attached. The hydrogen of H2SO4 will be taken over by the OH, leaves as H2O. Then the remaining reactions, H2SO4 in 410 Kelvin. The last reaction we saw 383 Kelvin. Here we are using 410 Kelvin. In that case, it will form ether instead of HSO4 addition, substitution. H2SO4 in 433 Kelvin, it will form ethene. So this differentiation of temperature is very, very important. Then comes H2SO4 0 degree. Here you can see first it is forming the first step of the first reaction has been formed. Then Grignard reagent, it is forming alkane. Sodium, since it is acid in nature, alcohol, so alcohol is acidic in nature, so it is giving us the salt to prove the acidity. Then with pyridine and CH3COCl, it is giving us C2H5OCOCH3. Then, as I told you, the Lucas test, which is very, very important. This can be given as a clue point or can be asked as a straight question. The many types you can expect. Then phenols. Phenols, the naming is also important. Here the important phenols. Cresol, orthocresol, CH3 group with OH, that is cresol. OH, CH3 is ortho to OH, so that is orthocresol. Then catechol, that is 2 OH groups, dihydroxyphenol. Meta position means cresol-cenol, ortho position means catechol, and para position means quinol or hydroquinone. Hydroquinone means the structure will be like this. Okay, so the names are also important. Then the preparation of phenol, we saw this reaction in Halo chapter as well. Dow's process, NaOH 300 atm pressure. As I told you, this can't undergo any substitution reactions easily. That's why we are applying more pressure and temperature conditions. The process is called Dow's process, and from diazonium salt it is forming phenol in the presence of H2SO4 H2O. This question is also asked in the previous year question paper. With Grignard reagent, oxygen is forming as phenol with MgBr+. Then with benzene, with vanadium pentoxide, it is giving us phenol. And cumene process, this is cumene. It will be looking like this. Cumene process, cumene is reacted with oxygen and the peroxide to form, first it will form cumene peroxide followed by phenol and acetone. This reaction with the byproduct is totally important. This total process is important. This can be asked as a several questions. What is the intermediate? Cumene peroxide is intermediate. What is the byproduct? Okay. So what is the structure of the reactant? So many questions were asked already in previous year papers. Then chemical properties. With bromine water, this part is important. Listen. So with bromine water, it is forming as tribromophenol. Tribromophenol. With bromine with CS2, it is forming ortho and para substituted phenol, separately substituted. Okay. So this differentiation you must know. And phenol with neutral ferric chloride. This is a clue point. Phenol with neutral ferric chloride, it gives purple color. The question can be asked, X is treated with neutral ferric chloride, it is giving us a purple color. Means you have to understand that is phenol. Okay. Then phenol with dilute and HNO3, again that will give ortho and para substituted product. And the question can be asked from here as well, picric acid. This is not having any carboxylic acid functional group, but still the name is picric acid. Okay. This is also known as 2,4,6 trinitrophenol. Okay. Then Scott-Bowman reaction. So Scott-Bowman means immediately this C6H5COCl benzoyl chloride should strike your mind. With phenol, that is giving us C6H5OCO C6H5. Because here I am having one phenyl group and another phenyl group is there in the reagent as well. Then another very important reaction, that is Reimer-Tiemann reaction. N number of questions can be asked from this reaction. Okay, phenol is treated with chloroform NaOH to give ortho and para substituted product. The major product is ortho-salicylaldehyde because of the hydrogen bonding. You can see the mechanism over here. CHCl3 treated with KOH to form carbenes. This is carbene. We very well know about the intermediate, is it? So carbene, this is getting attached. This is what the reaction flow is. The question can be asked from carbene as well. Okay, what is the intermediate formed over there? Then salicylaldehyde has been formed. Then CCl4NaOH, it is forming salicylic acid. Then Gold's reaction, phenol with NaOH CO2. Gold's reaction means there will be CO2. So CO2, 400 degrees, 400 Kelvin, 427 atm. It is forming again salicylaldehyde with CrO2Cl2. It is forming parabenzoquinone. Mistake had happened over there. So parabenzoquinone as a product. Then phenol with benzene diazonium chloride, it is forming as orange azo dye. So this is also a very important clue point. Then ethers. Ethers, the naming is important and some preparation properties. Very simple, very short. phenol, alcohol with H2SO4, 413 Kelvin, it is giving us ether. We saw this reaction just now. Then this next preparation, that is Williamson synthesis, where I'm taking alkyl halide with RONA. This is acting as a base to give ethers. So RO minus will attack the carbocation part. This follows SN2 mechanism to give ethers. The properties of ether, as you can see, with HI it is forming RI. With excess of HI it is forming 2RI with H2O. So these two differentiation you must understand. Then anisole, that is aromatic ether, with Br2 acetic acid, it is forming para and ortho substituted product with CH3Cl, AlCl3. Once again, that is in Friedel-Crafts reaction, right, to give para substituted product. So that is about ether group. Next, we are moving on to carbonyl compounds chapter. So in carbonyl compounds chapter, we have different carbonyl compounds like aldehyde, ketone and carboxylic acids we are going to see. So first, aldehydes. So aldehydes, as we all know, which is having CHO functional group, ketone, that is CO, RCOR. So this can exhibit metamerism. Okay, so be careful with that guy. Then if I'm talking about the preparation part, the naming part, just revise. The name of nomenclature questions can also be asked. We also included the nomenclature here, is it? So nomenclature part is also important in case of carbonyl compounds. Here you can see the preparation part, the first preparation with oxidation of alcohol. I'm giving you the trick. If I'm taking primary alcohol, one second. I'm taking primary alcohol, upon oxidation that will give aldehyde, and further oxidation that will give carboxylic acid. Similarly, if I'm taking secondary alcohol, upon mild oxidation that will give you ketones, and further oxidation that will also give carboxylic acid with less number of carbons. Okay, so that is the important part in carbonyl compounds chapter. Okay, so you must know what are those oxidizing agent, which is mild oxidizing agent, which is strong oxidizing agent. Mostly they will give the strong oxidizing agent as KMNO4 and K2Cr2O7, sometimes osmium oxide. Okay, so this particular reagent, Jones reagent, is for the conversion of secondary alcohol only, secondary alcohol to ketone. Okay, in case of primary alcohol, that will immediately form COOH, carboxylic acid. So we are particularly taking this for secondary alcohol only. Then hydrogenation with acid chloride. This is a very important named reaction, that is Rosenman reduction. So palladium is acting as a catalyst and barium sulfate is poisonous catalyst from RCOCl, it is forming RCHO. Then distillation, upon the release of CO2, it is forming aldehydes, and from alkene, oxo process to form aldehyde with one carbon extra because of carbon monoxide we have added. Then Gattermann-Gove synthesis, where we are taking benzene with carbon monoxide and HCl, which will give you aldehyde. Gattermann aldehyde synthesis, where I'm using HCl with HCl, that will give you immediately aldehyde. Then M1O2, that can also leave you with aldehydes. So these are some important reactions. The major important reaction is Stephan reaction. So Stephan, you can remember it, SnCl2, because there is another reaction which involves SnCl4. So here SnCl2 with RCN, that is giving us ammonia with aldehyde. And with Grignard reagent with Cn, which will give you ketones. Nucleophilic addition. So nucleophilic addition, it happens in around the acidic medium, pH of 3.5. Usually the very important stuff in nucleophilic addition is that 2,4 DNP reaction. Okay, this will be given as a clue point. The 2,4 DNP is giving positive, which means this free CO group is there. Okay, so that is an important clue point over here. Then comes our HCN. With HCN, this is forming cyanohydrine, OH group, along with that CN. Then NaHSO4, Grignard reagent, once again it is forming alcohol. And as you can see, I have listed the groups over here. NH2 with any group, another NH2, OH or 2,4 DNP or any other group, which will lead to the formation of the structure like this, hydrozones. Then oxidation reaction, Tollens and Fellings reagent. What is Tollens reagent? Tollens reagent is ammoniacal silver nitrate, and Felling solution is a mix of Felling A and Felling B, which is nothing but copper sulfate and sodium potassium tartrate. So with this, it will give you positive, means that is having aldehyde group in it. Okay, so as you can see, Tollens reagent, the positive result is showing of the silver mirror, or worst case that will give you the black precipitate. With Felling solution, that will give you the red precipitate because of the formation of CO2O. Okay, both the reactions, it's a oxidation reaction. As you can see, it is forming RCOO minus. Then the next one, so the reduction part, upon reducing ketone, it will give you secondary alcohol. Upon reducing aldehyde, it will give you primary alcohol. We already saw that. Clemmensen reduction and Wolff-Kishner, this is happening in the acidic medium. This is for acid sensitive groups. Okay, then polymerization. This part is important because this is forming a paraldehyde, metaldehyde, with depend on the number of aldehydes I am taking. Then the most important reaction in this chapter, that is aldol condensation. Aldol condensation means that should be a alpha hydrogen in the aldehyde. So we should be forming a aldol at the end of the process. That's why we are calling it aldol condensation. First it will form beta hydroxy aldehyde. So how the mechanism happens? The first step is formation of carbon ion, and then carbon ion attack with another aldehyde to form a reagent like this. Then it will form aldol. Alcohol with aldehyde, that's why aldol. So upon treating it further, it will form alpha beta unsaturated aldehyde. The next one, that is Cannizzaro reaction, it is also equally important. Here the condition is there should not be any alpha hydrogen. For example, here you can take benzaldehyde. It is undergoing the reaction with basic medium to form. This is nothing but the disproportionation reaction. Cannizzaro reaction is a disproportionation reaction. What is that? It is the same compound will get oxidized and then reduced. So aldehyde, upon oxidation, that will give you carboxylic acid. Upon reduction, it will give you alcohols. Okay. Then the mechanism, if you want, you can refer it to. I'm just attaching it. This following a dianion followed by the addition of another aldehyde. If I'm taking two different aldehydes, then it would follow crossed Cannizzaro reaction. Then condensation of acetone. Acetone just condensed to form a mesethylene and phenol, just a release of water. Hydrolysis of alkyl cyanides, just you can see H and OH will get attached. Upon hydrolysis of cyanide, it will give you carboxylic acids at the end. First that will give you amines, followed by that it will give you carboxylic acids. Then we are moving on to carboxylic acid part. So what are the derivatives we have for carboxylic acid? That is acid chloride, anhydrides, amines, and esters, right? So you can see the usual preparation. This we know from secondary alcohol also we know. Then haloform reaction, we already talked about this. And what are the compounds will give positive to the haloform reaction with carbonyl compound? That is, this should have a CH3 group attached with the functional group, directly attached with the functional group. So as you can see, this will give you positive, this will give you positive, and this will not give you positive to the haloform reaction. So if they are mentioning that this is giving positive to the haloform reaction, then you have to assume that this is having the CH3 group attached, directly attached with the functional group. So that is the clue point it is giving. So then the terminal trihalogen reactions, all three OH group will get attached over there, which is unstable. So it is forming releasing H2O to form carboxylic acid, and with CO2 with Grignard reagent, it can give you carboxylic acids. Ester hydrolysis, hydrolyzing esters, it will give acid, carboxylic acid and alcohol. This is very, very important, very basic also. Action of heat, what will happen? CO2 will get evaporated, then dicarboxylic acid will give you monocarboxylic acid. Then moving on to the post reaction, again alkene is giving us carboxylic acid group. So this reaction we already saw that in hydrocarbons part, the oxidation happens with potassium permanganate. This is a syn attack. Then the chemical properties of carboxylic acid. Since there is an acid, it can be attacked by the base or metal to form its salts. The important step over here is that with carboxylic acid, if I am treating it with sodium carbonate or sodium bicarbonate, it will release carbon dioxide. That carbon dioxide is from the sodium carbonate or bicarbonate, not from COOH. So the isotopic kind of question can be asked from this part. Then esterification, we very well know, and which will favor the primary, then comes secondary, then comes tertiary. Then the interesting question here, you can expect that this formic acid will undergo the process of dehydration or not. It will not undergo because of the it will not form the anhydride, it will directly form CO2 and H2O. So the answer is no. Then RCOOH with ammonia, it is forming amines at the end. With AlCl2, Al2O3, it is forming RCN. So I have listed some reducing agents and oxidizing agents as well. These are some reactions which carboxylic acid is undergoing. Among this, the ketene process is also important, and diazomethane is also important, which questions have been asked in the previous year papers. The named reaction, Siskimet reaction, which involves N3H. Okay, it's not ammonia, N3H. So it will give you amines and CO2 and N2. Anti-acid synthesis, it is a homologation formation. What is that? One extra carbon will be added over there in the product. So RCOOH is reacting to form RCH2COOH. Then Helen-Ohal-Zelinsky reaction, HVZ reaction, which is having the alpha hydrogens, like we said for aldol. with red phosphorus and Cl2, it is forming alpha halocarboxylic acid. This is important because there are so many reactions we have seen that is getting attached with the functional group, right? Here that is adding with the alpha hydrogen. Alpha hydrogen is getting substituted. One is substituted by our halo group. Then we came to the chapter amines. So it is a very small chapter, but at the same time you can expect some questions. Very important chapter as well. So let's quickly go through this chapter. The first thing first, amines, which is having NH2 functional group. The question can be asked from the basicity also, and also from the reactions. The reaction involves the first preparation is that Hofmann alkylation. We already saw this reaction. Upon adding excess of ammonia, it will give you primary, secondary, tertiary and quaternary amines as well. Then the second important reaction, that is Gabriel phthalimide synthesis. This is not for aromatic amine. This will give you the primary amines, alkyl primary amines. Then Hofmann bromamide. This is an important named reaction. 5-step process it involves. This is also gives primary amines. The reagent are Br2KOH. From amide, this is giving you amines. You can see one carbon less in the product. So we have seen 1, 2, 3 reactions where one carbon extra in the product. Here this particular reaction which is having one carbon less in the product. Then the reduction part. Reduction means nothing but the hydrogen addition. From amides it will give you amines. From cyanides it will give you amines. And for the preparation of secondary amines, you can take isocyanide to give secondary amines. Nitro, of course, that will give you amines. This is very, very important. Nitro is getting reduced to give amines. Then the properties of amines. The basic nature, before that, usually 2 types of question can be asked, in aqueous and in solid or powder state. So aqueous means tertiary will be more basic. Solid means primary. So secondary will be more basic. Solid means tertiary will be more basic. So thus you have to remember. Then the reactions involving basicity nature of amines. As you can see, the lone pairs of amine is donating. The lone pair of nitrogen is getting donated to other groups. With nitrous acid, RNH2 is giving us ROH. With aniline, it is giving benzene diazonium salt. Benzene diazonium salt will not be formed from the aliphatic amines because of lack of resonance. Okay, if that is reacting with secondary amine also, it will give you yellow oil liquid. These are the distinguishing tests for aromatic and aliphatic, and as well as the primary, secondary and tertiary amines. Then acylation reaction. Secondary amine is giving you tertiary amines, and RNH2 is giving you RNHCOR. Then with Grignard reagent, it will give you RH and the alkanes. Then carbamide reaction, which is equally important, with chloroform KOH, it will give you isocyanate. Mustard oil reaction with CS2, this is forming isothiocyanate RCNS. So remember the formula, guys, which is important. Then, as I told you, the distinguishing aromatic and primary, secondary and tertiary. This reaction with nitrous acid. Nitrous acid is nothing but we are treating nitric acid with base. So these type of transformations you can expect. Then finally, benzene diazonium chloride. Steinmeier reaction, Gattermann reaction, Ball-Schiemann reactions. These are important. And one more reaction I wanted to tell you, that is H3PO2. This will give you benzene. So this is the question asked 2 years back. So please be careful with that. Then beta naphthol, it will give you the dyes. These are some dye reactions for benzene diazonium chloride. These are some important reactions. Benzene diazoxide chloride has n number of applications. These are some important reactions of it. Okay, so that's it. So please do attempt the mock test. So mock test link I'm giving you in the description box, which will contain 30 plus mock test and 5 full test papers as well with the solution. Okay, please utilize that, which is given in the description box. So thank you for watching. Please do practice more and more test.